I was talking about line integrals at the end of last time, and we saw how to do a general line integral of this form. C is some curve in the plane or in space, and f is some function. And we looked at line integrals like this. And just to remind you of what we did, the way to compute this, I just want to think of this as sort of locked. You cannot compute it directly. Nothing. The ds is not like a regular s. It stands for something else. It's a line or curve length little interval there. So you cannot just do your standard integral tricks. You have to convert it to a regular one-dimensional integral. And the way we saw it is you parameterize. You take a parameterization r of t. So this is a parameterization, and v of t is its derivative. And then the formula that we used is that you convert this integral using essentially ds becomes the length of v of t dt. So that's the speed dt. So we looked at that last time, and that allows you to convert the integral into a regular integral with respect to t, which is just a real parameter. Okay, so no problems there. I did that at the end of the time. The other thing we looked at was the special case of capital F being a vector field, and I showed you how to deal with f dot dr, at least in 2 dimensions. And to remind you, it's very, very similar. You compute your r prime of t. Once you have r of t, you can also think of this velocity in the form dr, which is going to be r prime of t, the same vector, dt. It's just the same as the velocity, but we're writing it in a sort of differential way as dr as opposed to r prime of t dt. It's the same thing. And so this means that you could take your vector field f and write that in terms of t, something in t, vector in t, by substituting in the parameterization. Again, I did this last time, so I'm not going to do it again. But then you can directly put in f dot dr. And we did this, as I said. Now, that one other type would be something like this. F dot n ds. Now, this one was called a flow integral, or a circulation. It's circulation, goodness me, it's circulation if C happens to be a closed curve. Otherwise, it's just called a flow. And this one is a flux integral. Now, I'll show you how to compute it. But before I do that, it's sort of important to know what these things mean. You can probably do all the questions without actually knowing what they mean, but you still might be in a little bit of trouble if you don't appreciate what n is and what r is. So let me set this up as follows. Here's a curve C, not necessarily closed. Okay, now, the deal is this. The first integral, f ds, says we have a function. It's a scalar function, meaning at every point in the plane, say, there's a value. Now, actually, you don't care what the values are. Think of it as like a temperature. I don't care how hot it is here, 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 here. All I care is how hot it is on this wire or this little curve here. And this sort of adds up all the values. If you like, it's a sort of averaging thing. If you prefer to think of it that way, when you divide by the length of that curve, you do get the average temperature. So I'm sort of adding up all the temperatures along here. And F would then be the temperature. Okay, so that's what this means. Now, if you're going to write something like this, F dot dr, this is now a vector field, which means that in every point, you have a vector. So attached to every point, you have a vector. But actually, the vectors that are away from this curve you don't really care about. All you care about is the vectors on the curve. Now, when I say it's a vector field, the vectors have to kind of be in such a way that the ones with bases, as in the little hairs, if you like, near each other have to be kind of, the vectors also have to be close. You cannot have something in here that goes like this, right? That's not smooth. It's hard to get from there to there. I guess it's possible, but you'd have to sort of join them smoothly. But basically, you should think of it as a nicely combed hair, not exactly like my hair. but you know, it's just sort of not like tangled. Okay, so basically what we're doing then, for something like this, I'll redraw my curve here. What I'm doing in this integral is as follows. At every point on the curve, there are two vectors that are relevant. One vector is f, which is this, say, and the other vector is dr, which is in a sense the velocity vector. So this is f, say, and then this is the tangent vector v, or if you like, r prime of t, dr, with the dt as well. Okay, so what we're doing is taking the dot product of this. So we want f dot dr is essentially the dot product of this vector with this vector times dt. That's exactly what it is. Okay, so this is the dot product of these two, which means that actually f, what you do is you only really care about the value, the part of f. If you decompose it into a bit this way and a bit this way by using the projection, this part does not matter. It's only really this part times this part. So you're basically saying how much, as you move along here, how much of f do you experience in the direction that you're going? And you do that everywhere, and you add it up. So the f over here might be there, but if f is here, then you don't experience any of this. That's okay. Now everyone knows your ringtone. All right. If you're going, yes, general message. All right. So if you're going this way and the force is pointing this way, you don't feel it at all. You don't feel it. It's like a side wind, but it doesn't push you forward or backwards. So the dot product there would be nothing. Anyway, the point is you're doing it everywhere. You are comparing the direction of this f, whatever it is, to the direction you're going, which is v. And you are saying how much of the force, you take the dot product, it tells you how you're being affected by the force. And you add up to get the total effect. That's what the integral is. All right, so that's what that is, roughly speaking. And again, it's nice to have an interpretation of it because this makes an integral like this, f dot n, make a little more sense. You start off with the same vector field f, but this time instead of taking the dot product with the direction you're going, you're taking the dot product with a normal. So let's suppose we have a unit normal. So in this place, it looks like this. So it's got to be consistent. I can't switch to that normal here. I have to pick one of the two normal directions. So these are all the n's. Now n here is a unit normal. Now you might ask, why do I go dot dr and n ds, dot n ds? Why don't I put the ds here? Well, the reason is because this dr, as we saw, is like a v of t dt. And in fact, this is not a unit. This is not a unit tangent vector. This is a unit normal vector. If you want to be precise, you should really do this. You can make it into a unit vector as follows. You divide by v of t, and then you have to multiply by v of t. This is the length of the velocity. So when I say dr, that's the same as v of t dt, the vector, which is the same as the normal tangent vector of the unit, sorry, not normal, the unit tangent vector times its length dt. But this, of course, is just ds. So the reason you can get away without this ds stuff is because you've sort of ds puts the length and then you undo that. And so this dr is not a unit vector, but n by convention is the unit normal, so you need the damn ds. Okay, so notice these are all length 1, whereas the tangent vectors I drew here are not all the same length. Anyway, the point is that now we are taking f dot n, which is actually this part of f that matters. So the part that's going only sort of away from the curve matters. So the reason this is useful is you've got to imagine that you've got a whole army of ants along here ready to go through the curve, cross the curve, flux through. not along. That's not a flow, it's a flux. And they're going through, and there's this wind blowing, and some of them will be blown through with nice force, and if F over here is like this, then that will actually blow the ants away, and they have to resist more. And you want to know what is the total effect on all the different little ants of all these pushes. Some of them get pushed strongly. The more F is in the same direction as the normal, and the bigger it is, the more strongly they get pushed over the line. If it's pointing that way, they get pushed back, and it's like the wind's in their face. But if the wind's blowing this way here, that ant doesn't experience any force and can just sort of march across. So you've got to ask all the ants, was it easy? How good? Oh yeah, nice wind. Okay, no, it was. And you ask all the ants and you add them all up, and that's what the flux is. Okay, and this is particularly useful when your ants are, say, in a loop, and then you see how many of them get through. Of course, some of them get blown back, and you've got this inexhaustible supply of ants, and you can work out whether there's a net flow of ants out or in of the loop. You know, some of them will get out, but that will balance. You know, there's ants all over the place, and they get replenished from inside. We'll use a gas instead of ants, because, you know, winds don't normally blow ants around, but gas molecules. But I kind of like ants. Okay, so, I mean, only as an example. I don't really like ants. Anyway, so that's what these things are. And I think it's important to understand at least how the normal looks, especially because you're going to be talking about outward normals versus inward normals when you have a closed curve. Anyway, let me show you the computation of this thing. Come back over here. The formula that you need, okay, so let's just put this in perspective. In 2 dimensions, we had R of t is sum x of t comma y of t. So you've parameterized the curve C, by t, and you know what x is in terms of t and what y is in terms of t. And I'm using the formulas dr of t is x prime of t. So you just differentiate. This is what I've said above, dt. And that tells you how to use this one. But what about n? Well, basically, the best thing I can tell you, and this fixes up all this unit vector stuff that I was talking about. Everything works out. So n of t ds, a nice formula for that, is you essentially just switch these around and put a minus sign. Y prime of t minus x prime of t dt. So this is normal to this, because if you take the dot product, you get this times this minus the same thing. So it's x prime times y prime minus x prime times y prime. So the dot product is 0. This is perpendicular to this, and what's more, it has the same length. It has the same length. So it's exactly what you're looking for. Okay, this is not the unit normal. This is not the unit normal. You have to divide by the velocity, or the speed rather, to get the unit normal. But you don't need to, because the ds, it restores that speed and they cancel out, as I described over there. So that's the formula that you need. And another way of writing it, which is extremely simple, so let's recast these two formulas. Alternatively, I'll squeeze it in over here. dr is just essentially equal to dx comma dy. That's another way of looking at it. Whereas n ds is equal to dy comma minus dx. So that's pretty useful to know. So if you actually have to compute one of these things, the only question is whether the normal is pointing one way or the other. So you have to watch out here that maybe there's a minus. So perhaps I should put a plus or minus here. This is what you have to be careful of. There's an ambiguity as to which way is the normal, and you have to read the question. So I have to put it here as well. Okay, so let me show you how to use this formula in a fairly sort of straightforward and simple manner. So suppose that, well, again, I haven't seen sort of basic examples. There are examples that reduce to this, but suppose you have something like this. I'll give you a vector field in the plane. Say it's just x comma xy. And the curve C is the unit circle which is x squared plus y squared equals 1. And I want to compute, and again, this is now a closed loop, so you put the little circle in to indicate that you're going around once counterclockwise. I want to compute this, f dot n ds. Without using any theorems, I just want to compute it directly. Okay, so the way to compute this is as follows. So you take your favorite parameterization. I'll use t. So x is cosine t, y is sine t. Okay, so in other words, r is equal to cosine t sine t. Now, according to my formulas, I'll do this all differentially because it's really nice. According to my formulas, n ds you can write in differential form as dy comma minus dx. So you actually don't even need this line here. I'm going to erase this because it's sort of, that's good for the dr integral. But n ds, by what I said, is dy comma minus dx, which is dy is cosine t, and minus dx, well, if you differentiate cosine t, rather, you get minus sine t, but there's an extra minus, so you'll just get sine t dt. So that's your n ds. On the other hand, you've got to be careful about f. What's f? Well, f is x comma xy. I'll write it up as x comma xy, and x is cosine t, while xy is cosine t sine t. So this integral becomes as follows. F is, well, I need a little bit more room. This integral, f is cosine t, comma, cosine t, sine t. And then I have to dot that with dn, which I just, or nds rather, which I computed is cosine t, sine t, dt. And if I'm going once all the way around the circle, then t goes from 0 to 2 pi. And then I just have to take this dot product. It's going to be cosine squared t, so this coordinate times this coordinate, plus sine squared t cosine t. And that integral you can certainly do. I'm not going to do it. You need a double angle formula there and a substitution there. But the point is, I've reduced this rather impenetrable looking object into something that's completely tractable using Math 104 methods. Okay, so the main thing is to do f dot dr, you do dx comma dy, but to do f dot nds, you do dy comma minus dx. And that's this formula. Those are exactly those formulas here. The only thing you have to really, you should be trying to be careful about is whether maybe we got the direction wrong. Let's just do a reality check. Here's a sanity check for what we just did. What I'm claiming is that nds is cosine t sine t dt. So let's just check this. What this says is, here's the unit circle, here's the point cosine t sine t, right, on this. And I'm saying n is really the same thing, which makes sense because this vector, I just am now going to attach it over here. Okay, so no matter where I am, the vector, the normal that I've chosen, points in the same direction as the point. And that makes sense because we know the tangent's perpendicular to the radius. So the radius is the normal. So what this is the outward normal. Everywhere, if you repeat the same argument, it's an outward unit normal. It's clearly unit because cosine squared plus sine squared is 1. But, you know, if it said compute this integral where n is in fact the inward normal, then you'd have to take the negative of this vector and you get the negative of the same answer at the end. So I just want to emphasize that if you get the normal wrong, there's only two normals, the out and the in. And that's it. So one of them is the minus of the other. Okay? Now, if you're going to go counterclockwise in this integral, which, you know, it would be really sneaky. I guess they might go like that. But I couldn't believe that they would just do that because it's so hard to see which way it's going anyway in a tiny little circle. So they would say where it's going clockwise and make it make it bold. Well, then also you have to go in reverse. And the reason you have to go in reverse is you'd have to change the parameterization. This parameterization automatically goes counterclockwise. You know how it goes. It starts here and goes around once. If you want it to go clockwise, you have to do something like put a minus sine t there. Or actually, you can even switch it around to sine t comma cosine t. That will start up here and go around clockwise, if you think about it. So the point is that if you're going around a different way, you have to change the parameterization. If the normal is inward or outward, then you have to change, you have to put in a minus there. That's what it would be, minus. So careful here. Plus, and I checked it. I checked it by drawing a little picture. Okay? In fact, I didn't check it the first time I did it. I was filled with remorse for not checking it. All right? Any questions about the sort of basics of line integrals, computing them, as opposed to sort of any of the other stuff we're going to talk about later? Yes?
Can we instead actually change, instead of the integral going from 0 to 2 pi, can we make it go from negative 2 pi to 0?
Okay, so the question is, can you go from negative 2 pi to 0, or say negative pi to pi? Sure. As long as you go around the circle once, it'll be fine. In fact, there are many different parameterizations, and one of the beauties of this, which is really a chain rule in disguise, is that as long as you pick a parameterization that goes once around counterclockwise, no matter how fast it could go, like in any sort of speed you want, you get the same answer. You actually get the same answer, unless you make a mistake, in which case you could get anything, but it wouldn't mean anything. All right, so yes, there's a lot of built-in in the parameterization, and it's totally not obvious going into it that you should get the same answer, but you should. Any other questions? All right, so now there's one little sort of side topic that wasn't covered in my diagram yesterday. Yesterday, right at the beginning, I drew a sort of big old diagram, which I probably could have fit on these slightly bigger blackboards, I think. But never mind. It showed all the relationships between the different types of integrals. Well, now I'm going to deviate from that, and I need to tell you a little bit about conservative vector fields. Okay, so here's, again, this is by no means any sort of attempt to give you the full theory or justification, but here's what you have to know. So we say a vector field, so here are the main points. Let me see if I can get this in the same order that I want. So we're working in a nice region. We want to work in a nice region. And this is sort of important because sometimes there are some nice trick questions that show you examples where the region is not nice. So what do I mean by nice? I essentially need it to be connected, which is one piece, as opposed to two separate blobs, which would not be connected. That's not nice. And I also need it to be simply connected, which is not the same thing as just really easily connected. Simply connected means no holes. So none of this. No bagels. No good. So that's not nice as far as we're concerned. So we're working in a nice region. By the way, the region could be in the plane or it could be in space. And if it's a space, then you don't want any sort of holes of any sort, be it like a, so I'm thinking of a hollow shell, like a thick hollow spherical shell. That's no good because the interior is a hole. Even though you can't see it from the outside, it's in there. It's a hollow thing. So that's no good. You can't have that. By the way, a very common example is where the domain is everything but one point. Everything but one point, as in not the origin, say. That's no good. That's got a hole. It's only the size of a point. It's a pinprick hole, but it's still a hole. So, for example, R minus the origin is no good. Or rather, if you do use it, you have to disregard everything that I'm going to say. So you have to be very careful to work somewhere with no holes that's in one piece. So if you're working in a nice region, then the definition is that a vector field F is conservative if the integral of f dot dr, which is our standard sort of work integral or flow integral, c only depends on where c starts and finishes, i.e. path independent. It doesn't matter how you get there, it only matters where you start and where you finish. And that is not true for most f's. So you're working in this nice region, I want to integrate f dot dr, there's c, there's c1, there's c2, and it doesn't matter, you should get the same answer if f is conservative, as long as you start here and finish there. So that's conservative. Now, there are some nice other equivalent conditions. So, equivalently, it's good to be aware that this is the same thing as saying that the closed, so the integral around a closed loop is 0 for any loop. And the reason it's equivalent, just in a nutshell, is this. Suppose it's the same if you go this way or this way. So you get the same number. That means if you go backwards along one of the ways, you get the negative. So if I go here and I get 5, and I go here and I get 5 for my integral, then if I go here I get 5, and then back again I get minus 5. So when I've gone and retraced my steps, then I've made a closed loop, everything cancels, and I get back to 0. So this is exactly the same thing as this. Now, that's very important and very nice, but it doesn't tell you how to check that a field is conservative. And luckily, there's a very nice test, and it involves taking the curl. So, once I get a little bit of room to work with, all right, so what we're going to do is take the curl of the field. So another way to check you need the curl of f equals the 0 vector. Now, I have a little caveat about saying the curl. Technically, f has to be a three-dimensional thing for this to be relevant. It needs to be three-dimensional. You cannot take the curl of a two-dimensional field. So if f is, so note, if f, capital F, is two-dimensional, then you kind of have to stick a third component of 0. Put in a z coordinate of 0. And I'll show you an example of that. Will I? I'd like to. I don't really have an example of that. So as an example then, e.g., if f is just a two-dimensional vector field, if f of xy is the vector field, say, x squared y comma y cubed, then you have to sort of cheat, pretend that f of x, y, z is equal to x squared y, y cubed, comma 0, and then compute the curl. That's just a little comment. So if you're working in 2 dimensions, you might as well pretend you're in 3 dimensions with the third coordinate of 0. Then you can take the curl, and I'll be taking a few curls in examples. There's only one more piece of this theory. There's one more piece of this theory that you need to know, and then we can even do all the examples. So the last piece of this whole conservative business is as follows. If f is conservative, and this is sort of important, then it is the gradient of some potential function, a scalar function. It's called a potential little f. That's a scalar. And you find it by compatible integration, which that's my nickname for it. It's best described by examples, and this will come to. But once you've found it, then you have a beautiful piece of theory as follows. Then if C joins the points A to B, so C is a curve joining the points A to B, then we have this lovely formula for the integral of f dot dr, which is, it's just the potential at the end minus the potential at the beginning. There isn't, the potential is related to potential energy in a sense. So if I'm raising this piece of chalk, I'm actually giving it potential energy. I move through from a lower potential line to a higher potential line. So all this comes from physics. But without much ado, let me just say that another form of this formula that I've seen that you should be able to quote directly is that, remember, f is grad little f. So that means that another way of stating this formula that does not involve this vector field directly but only indirectly as the gradient that you need to know is that if you take the divergence of little f, that's a vector, not the divergence, I'm sorry, the gradient of little f, grad f dot dr is equal to f of b minus f of a. So that's an equivalent formula, but I've seen it directly, and you might not even be aware that this is about conservative vector fields, and you might get a little confused. So don't be confused, just learn both of these. Learn both of these. Here, f is, of course, as I said, the gradient of little f, so it's the same formula, but they come up in slightly different ways. Okay, so there's the theory that you need to know. Conservative is path independence. The way you check it is the curl. And then once you've got it, you can find the potential by integration and use that as an antiderivative in the way that you're used to, in a sense, for regular calculus. That's the whole theory in a nutshell. I'm going to do two examples, but first a question. Okay, so to put this in perspective, the last line right here holds for any function little f. This is true for any little f, scalar f. It doesn't have to be conservative because the gradient of f is automatically conservative. So actually, they're the same thing. The gradient of f, little f, is automatically conservative, and every conservative vector field is the gradient of a little f. They're the same thing. It's not obvious, but that's the theory of it. Here, capital F has to be conservative. I'm sorry, is it because... Okay, so the question doesn't really make sense. I'm not going to repeat it for the video because let me say that simply connected is about where it's defined. It has nothing to do with the function. It's just a set property. It's just the fact is that most functions, most vector fields are not conservative, and therefore you cannot possibly expect to have a formula like this being true because then you'd need to know which curve you had. See, the point is, here it is in a nutshell. That integral only depends on the endpoints of the curve. So that's automatically, this has to be conservative. You can see it directly from the formula, that this would not even possibly be true if the capital F was not conservative. Because, again, it only depends on where you finish and where you start. All right, let's look at some examples. So again, these come from previous finals. I've got two nice examples. that illustrate the main points. All right, so the first example is as follows. So it says, what does it say? Which one do I want to do first? Let's do this one first. So you're given a vector field F, which looks like this. AY squared plus 2CXZ, comma, BXY plus CYZ, comma, AY squared plus CX squared. Okay, where A, B, and C, little a, b, and c are all constants. And the question is, for what values or what possible values of A and B is F conservative? What do you need to have for these numbers A, B, and C to make that conservative? That's the first part of the question. So I'll do that first before I tell you what the second part is. So the answer to this is as follows. So you take the curl of F, treating, of course, A, B, and C as constants. So the way you do this is you set up the regular determinant matrix, 3 by 3. Curls are always 3 by 3. And here you do a ddx, ddy, ddz. And then finally, you plug in these values, ay squared plus 2cxz in that entry, bxy plus cyz here, and here we have ay squared plus cx squared. All right, now we just compute this like a determinant. The I-coordinate is, you take ddy of this, which is 2ay, minus ddz of this, which is minus cy. Okay? For the j-coordinate, you need the negative of this ddx of this. So that's going to give us a minus 2cx. And then we're going to have minus, minus, so it's going to actually be plus the z derivative of this, which looks like a 2cx. That's the j. Yeah. I should be more careful here. Plus j minus 2cx plus 2cx. And then finally the k-coordinate is going to be the x derivative of this, which looks like it's by, minus the y derivative of this, which is 2ay. Okay, so this is equal to 2a minus c y, comma, that's just 0. I'll write it as a vector now. Comma, 0, comma, and then the k-coordinate is b minus 2a outside of y. Okay, so that's the curl. That's the curl. This has to equal 0 for all x, y, z. The only way that can be true is if 2a minus c equals 0 and b minus 2a equals 0. You absolutely need that 2a equals c and 2a equals b. Well, if 2a equals b and 2a equals c, then you might as well write 2a equals b equals c. So it doesn't matter what, you have one degree of freedom. If you know what c is, then you know what b and a and c are. All right. Question before I do the second part. Right, so the question is, can you not just do what I have called here compatible integration? The answer is yes. It's possible to come to the same conclusion. It might be a little more messy. So the curl method is sort of recommended. It's sort of more reliable, but yes, you could do it by this integration method and see if you can make it work. I just prefer to have something concrete and definite. Now, to see what that means, let me show you what the second part of the question is. So the part 2 says this. There is a curve that is given. Let C be the curve, parameterized as follows. T squared t cubed e to the t, where t is between 0 and 1. So it's a pretty nasty sort of curve. I have no idea what it looks like in 3 dimensions. It's some bizarre path. But you're asked to find f dot dr. Actually, the question said f dot t ds. But from what I said, this is actually the same thing as this. That's an alternative notation where t is the unit tangent vector. So just be aware that if you see that, this is what we're using more commonly, but that's possible as an alternative notation. All right, so the question is to find that where f is the same vector field in there in the case where it's conservative. So it said when it's conservative for those values of a, b, and c, compute that. Compute that. So the way to do this is to use the formula f of b minus f of a, where we have to find all 3 of these things. We have to find little f, we have to find a and b. Well, let's do the simple thing first. A is the beginning. So to find a, you set t equals 0, and you get 0, 0, e to the 0. Or to be precise, 0 squared, 0 cubed, e to the 0, which is 0, 0, 1. And to get b, you set t equals 1. And you plug that in, and you get 1 squared, 1 cubed, e to the 1, which is just 1, 1, e. So we now know what a and b are, but we do have to find the potential f. And this is now an example of what I had called compatible integration. So we're going to assume, of course, that 2a equals b equals c. So if we do that, then f looks like this. So we may as well work in all in terms of, say, I don't know, what's your favorite one of A, B, and C? B? Okay. But no, I heard B first. We're going to work in terms of B. In terms of B, if that's true, f is now equal to, well, a is b over 2. Do you really want to deal with halves? I've changed my mind. We're going to deal with a. Yes. Hey, my name is Adrian, and my last name is Banner, so I'm just biased against C. Although actually my sister's name begins with C, so there you go. Anyway, enough babbling. F would then be ay squared plus 2cx, but c is 2a, so this is actually going to be 4axz, comma. B is 2a as well, so you get 2axy, plus c is 2a as well, 2ayz. And then finally you have ay squared plus 2ax squared, because c is that. So what we need to do is we need to find this. We need f is the gradient of little f. So in other words, this has to be equal to df dx. This has to be equal to df dy. And this has to be equal to df dz. So you're looking for a little f that satisfies all of this. Df dx is this, df dy is this, df dz is this. So when I say compatible integration, I always take the x coordinate and integrate it first with respect to x. So take the x coordinate, integrate that with respect to x. And so we're going to start mapping out that f is equal to, I integrate this and I get ax y squared, because when you integrate a constant with respect to x, you just get x. Here I get 4ax, the integral of x is x squared over 2. So here I'm going to get plus 2ax squared z. So this is from the first integral here. So I just integrated that with respect to x. Now I integrate this with respect to y. And I'm going to do it term by term. And now here's the trick. If you have a term that is already included, then you ignore it. But if it's a new term, then you keep it. So I'm looking at this, and I'm now going to integrate this with respect to y. Okay, the integral of y is y squared over 2. and again, y squared over 2. So this piece will give me axy squared, but I've already got that. So this one I already have. When I integrate this, on the other hand, I have ay squared z. The 2 goes away. The integral of 2y is y squared. And I haven't seen a piece like that before. So I just have ay squared z. So this piece gave me this. This piece gave me this. This piece also gave me this. Now, one way to tell if you're going to get a brand new one is whether this involves an x or not. If it involves an x, then you better get something you've already used. Because then when you differentiate with respect to x, you've got to get something here. It's only this term, which has nothing to do with x, that could possibly give a new term. And similarly here, over here, well, when we integrate this with respect to z, we'd absolutely better get something we already have. And same with that. It's only the stuff that doesn't depend on x and y that can possibly give us anything new. So if there was like a z to the 5th here, then that would be okay. But as it turns out, there isn't. When you integrate this with respect to z, so we're going to take this and integrate with respect to z, and when we do, the ay squared gives me this, and the 2ax squared gives me this. If you get something that does not match, then you screwed up the first step. You're not dealing with the conservative field. And so the question that you asked before is, can't you just see if you can construct this, and if you can, then it's conservative? And the answer is yes, but remember, you'd have all the A's, B's, and C's, and then you'd have to sort of match them, and it's a much, much easier thing to do in this problem because you have all these unknown variables to take the curl. That's why I recommend that method. You can try it. Anyway, there's only one other thing that we could put in if we want, which is a plus C. But you don't have to. The question is find the integral. You don't need every potential function. You just need one. So that's optional. You know, when you do an integral in regular calculus, you don't put the plus C for a definite integral. It doesn't matter what C you use. Anyway, so does anyone have a question about how I got that? Is there anything unclear about what I just did? Does it make sense? Just do the x integrals, do the y integrals, just grab the matching terms and put them together. Anything that doesn't match, add it, and then the z integral. And the more, like by the time you get up to the z integral, your hands are almost completely tied. All right, so then we can finish the problem. So this integral, f dot dr, is f of b, little f of b minus little f of a. And so finally, I have to take this nasty function and plug in 1,1e. So if I plug in 1,1e, I get a times 1 plus 2a times 1 times e plus a times 1 squared times e. That's f of b minus, what's f of a? Now I have to plug in 0, 0, 1. So I get 0, 0, 0. And all that works out to be a plus 3ae. And you don't know what a is, so you have to leave it. You have to leave it. That's the one little bit of ambiguity. All right. What do you think of that? Does that make sense? Question?
Going back to that board,
yeah.
the curl magnitude of the curl is 0.
Not just the magnitude, but all three components have to be 0. It has to be the 0 vector.
Okay. Well, I mean, isn't that the same kind of thing?
Yes, the only vector that has a magnitude of 0 is in fact the 0 vector.
Okay.
But it's easier, rather than squaring the thing, it's easier to just set them all 0.
Right.
Okay. Any other questions about that example?
We parameterize the vector field.
How are you going to parameterize it?
Will we be able to do that?
We don't really parameterize vector fields.
No, like, I mean, let's say we have t squared t, x equals t squared, and then we just plug that.
Oh, you mean compute this integral directly?
Yeah.
As in, what you do is you actually compute dr as 2t, 3t, e to the t dt, just 3 squared t by just differentiating, and then dot producting it with the f, Yeah, I mean, you know, you'll probably be integrating by parts about 10 million times, but otherwise it makes perfect sense. When you have a conservative vector field, it's always easier to do it. Well, mostly easier to do it that way. All right, I better give you another example. This one is quite a nice example. Okay, come on. Okay, enough. Okay. F of x, y, z is given as minus y over x squared plus y squared, x squared plus y squared, comma 0. Okay, and so what you have is you have C1 is the circle x squared plus y squared equals 1 and z equals 0. So we're working in 3 dimensions, but this is a circle contained in the xy plane. And so the first part is to compute f dot dr for this C1. So compute that directly. Well, we probably actually have to do it. We have to do it. So I'm going to say x is cosine t, y is sine t, t between 0 and 2 pi. So this is all very familiar. In other words, r of t is cosine t, sine t. So dr is the derivative minus sine t, cosine t, dt. Now what is f? F then equals, I take this vector field and I plug in y is cosine, y is sine t, x is cosine t, and the bottom is 1. X squared plus y squared is 1. So you just get minus sine t, comma cosine t. So f dot dr is just this dot this. So it's sine squared t plus cosine squared t dt, which is just 1 dt. So this integral is just the integral from 0 to 2 pi of 1 dt, which is 2 pi. All right, that's nothing to do with conservative vector fields, that's just a computation. All right, any questions about that computation? Of course, the real meat is in the next part of the problem. Okay, so the next part says this. Find well, in order to do this, you have to set up the same thing, and I'm not going to do it. I'm just going to leave it to you to set this up. You do it. Sorry. And you find you get 0. You'll find that you get 0. It's not as bad as it looks because there's no z, so the ddz parts are not particularly interesting. But you'll find that you get the vector 0, as in 0, 0, 0. So the question is, part C, is f conservative? Explain. Okay, so we have 2 pieces of evidence. One is that its curl is 0, which you can compute for yourself, as I said. And another is that the integral around the unit circle in the xy plane is 2 pi. So is it conservative or not? No, it can't be conservative. So remember, the definition of conservative is that the integral around any closed loop is 0. And here you've got a closed loop, and the integral is manifestly not 0. It's 2 pi. So how does that jive with this? What's the answer? Yes, there's a singularity. So the domain, actually no, domain is not nice. Domain has a hole. The domain looks like this. In space, you cannot have the z-axis. So this is bad. This is no good, not in domain. So x equals y equals 0. Z-axis not in domain. Because if x and y are both 0, then the denominator of f would be 0, and you're not allowed to have that. So you're not allowed to have not just the origin, but actually anywhere on the z-axis. And the loop that we're dealing with goes nicely around that pole. No good. No good. So that explains the discrepancy. On the other hand, part D says this. You have a triangle. Consider the triangle C2. I'm going to call it C2, and it has vertices 1, 1, 1, minus 1, 1, 2, and 0, 2, 3 in space. So it's some triangle in space. And the question is, find, again, C2, the circulation, f dot dr. Okay, so here you could definitely make 3 different parameterizations for the 3 lines. You know, you use t, take the difference vector. That's all pre-midterm stuff to find parameterizations of lines and line segments. And then you could actually compute this. But again, you know, all this conservative stuff should make you think that actually probably there's an easier way. And the easier way is this. Imagine that you have a curve out here that does not, in fact, have anything to do with the singularity. What's the circulation integral for there? It's 0. Now, why does this not pose a problem? Well, what you could do is just work in a domain like this, which is nice, that includes the curve that you care about, that does not touch the bad bit. So you sort of reduce the domain. Here the curl is 0, so any loop contained in there, since it's a nice domain, doesn't have any singularities, no problems, it's no holes, any loop in there will have integral 0. So hopefully this will be 0. All you need is that this triangle does not enclose the z-axis. This will equal 0 for any curve not going around the z-axis. Because f is conservative, then on that curve or a neighborhood of that curve. As long as the curve avoids the x-axis does not go around it. You're not allowed to. The stick of the curve cannot, of the z-axis cannot poke through the hole of the curve. All right? So how do you know about this triangle? Well, you just need to do a little bit of geometry, but not very much. Actually, the z coordinates don't even matter. It's only the x, y coordinates that matter. So here it is. 1, 1. Just take 1, 1. Take minus 1, 1. And take 0, 2. Okay, so the actual triangle that you want, if the z-axis is coming out of the plane, this is the bad axis. We're trying to avoid that. But the triangle is sitting above here. It's sort of, it doesn't matter what the z-coordinates are. 3, 2, 1. The triangle's just going to sit here, but the z-axis doesn't poke through it. The only way the z-axis could poke through it is if when you took the projection by ignoring the z-coordinate, it contained the origin. Then the z-axis would go through. You see, if the 3 points were here, here, and here, then no matter where they were, no matter how far out or into the board along these lines, the z-axis would go through that triangle. Okay, so basically, our triangle doesn't. So the integral, so the answer is 0, not a vector 0. Okay, much, much simpler than computing it. You just say, the curve doesn't enclose the singularity, f is therefore conservative around that curve or in that neighborhood, and therefore the circulation integral is 0 because it's a closed curve. Okay, any questions about that? That took me a while to do this. I don't think I'm going to finish early. Go ahead.
I just don't see how the curl of f, how did these help you understand that each is
Conservative?
conservative?
So the question is, how can you see that a vector field is conservative if its curl is 0? And the answer is it's straight out of Stokes' theorem. The proof is one line once you've seen Stokes' theorem, which hopefully we will soon. All right, any other questions about this conservative stuff? No, okay. The next thing to talk about is surface integrals. This is the last type of integral. I will tell you how to compute it. I will do a few examples, and then all that's left is to do Green's theorem, Stokes' theorem, and the divergence theorem. And you will see that the theory is small. However, I'm not going to take a break until 9 o'clock. It is only 8:34. So we go on with surface integrals. Okay, like a line integral, you start off with something that looks a little bit weird. You start off with something that looks a bit weird. It's the double integral of f, but instead of dA or dx dy or something familiar, you've got this nasty d sigma, where d sigma is a little piece of area. It's a little piece of surface area. Again, like the line integral, you have to unlock this to compute it. This is not something you can compute even as a double integral without doing extra work. So you have to convert it into a double integral. Unless, of course, you use one of the fancy theorems that I'm going to talk about and change it into something else. If you're going to do this directly, you have to convert into a double integral. And there's two ways of doing it. Into regular double integral. With some crap over there. All right, so two methods. Method one. Okay, so actually, I'm going to change this to a g. It doesn't matter what it's called. It's some integrand there. The reason is I want to use little f, just to be consistent with the textbook, essentially. So you need a way of describing s. You need a way of describing s. So method one says, describe s like this. F of x, y, z equals 0. Or it can be a constant here, but you can always throw the constant on the other side. So I'll just describe it as the 0 set of a function. And very often you see this. Very, very often you see this. So, or a constant, that's fine. Doesn't matter. All you're going to do is take the derivative. Okay, so you describe f like this, and here's what you hope. You hope that for each value of x, y, there is one z. At most, one z. Okay, so here's the picture that you should be thinking of if you use method one. Your surface is sitting over here. It casts a shadow on the xy plane. So this is R, the shadow on xy plane. And this is the surface S. And what I hope is that, gee, my perspective is not very good. What I hope is that for every point here, there's exactly one point on the surface. Different heights. Okay, so essentially z becomes a function itself of the other two, i.e., you can solve f of x, y, z equals 0 as z equals something x, y stuff. Okay, so before I go on with the setup, what if you cannot do it like this? Suppose you have a sphere, for example. That's the easiest example I can think of where this would seem to be a problem. So, if your picture looks like this, if you have a sphere, then at some point in the shadow there's actually two values of z. So that seems to be a problem. Well, if there's more than one value, if not, then break it up into two surfaces and repeat for both. Then there's only one z here, and there's one z there. So you just break up the surface integral into two separate integrals. That's pretty rare. I haven't seen a lot of problems which actually required you to do that using this method. Method 2, by the way, which is a parametric method, doesn't have this weakness, right? Sort of the analog is when you write y equals f of x, the thing has to be a function. But when you write parameters, the curve doesn't have to be a function and can even cross itself. So that's the analog. Anyway, so if necessary, by breaking up into separate integrals, we can hopefully get the thing in this form. Then how do you actually do the integral? Well, there's a very important formula that you simply have to memorize. I'd love to have time to justify it, but I didn't even when I did my regular session, so I certainly don't have it now. D sigma is the thing that you care about. You need to convert it as follows. It's grad f, the length of that, divided by grad f dot k, absolute value of this, dA. Where this has a certain meaning. So little f is the function of the surface. And again, by way of explanation, little s is the function f of x, y, z equals 0, or a constant. Doesn't matter. K, as always, is the vector 0, 0, 1. Don't forget that. You can look at this and say, what's the k? K is just the z direction. And dA lives in the shadow, R. So the whole sort of impact of this is that you've converted as follows. So here's how the full conversion works. You have this integral g d sigma over the surface. So this method says as follows. You convert it into a double integral over the shadow region in xy plane. And you're going to have g of x, y, and z. But you have to be a little bit careful. In a second, I'll show you the d sigma is what I just wrote up. And then I'll change the dA into a dx dy. That's the same thing.
How do we get k?
K is 0, 0, 1. Don't ask how you get k. K is 0, 0, 1. It's always 0, 0, 1. As a vector, that's what it is. Okay? Never anything else. At least not until next week. No, it's always 0, 0, 1. Okay. Next week you won't really care that it's 0, 0, 1, I suspect, but that's what it is. All right. But this does bring up a nice point. This is a vector on the top. So this is the length of a vector. This, on the other hand, is inside here a scalar. Because when you take this and you dot it with 0, 0, 1, this is just the z coordinate. So even if you don't like the k, you're just the z coordinate of grad f. So this then becomes just a regular absolute value. Absolute value of scalar. So it's a sort of confusing formula in a sense that this is a length and this is an absolute value. Of course, they're the same thing if you think of this as a one-dimensional vector, but let's not get so esoteric. There's one other very important point about this. Any z's remaining in either of these terms have to be eliminated. So you have to eliminate z from this. And that's why I said you have to be able to solve z in terms of x and y. See, this integral is only dx dy. You don't want any stray z's. So any z's coming out of there or here, for that matter, have to be replaced by some function of x and y. When all's done, this is all boiled down to some function of x and y, dx dy, and it's a normal double integral. Normal meaning not unit normal, but just ordinary. It's an ordinary old double integral. Okay? Sounds tricky, but it's not so bad. I'll do an example. All right. Where's the example? Okay. So the example I have in mind is this. Find the surface area, SA, not South Australia, in case anyone was wondering. I doubt that you were. The surface area of Z equal x squared plus y squared, where 1 is less than or equal to Z is less than or equal to 4. Okay, so from what I said yesterday, a surface area, let's call this S. Let's call this whole surface S. So what we need is a surface integral over S with an integrand of 1. No one is going to tell you that you have to write down a surface integral, but that's what you have to do, and then find it. Okay? To find a surface area, you write down a double integral d sigma, but with a 1 as the integrand. You're not integrating a function at this point, you're just integrating 1. Okay? Well, 1 is a function, but it's a very straightforward function. Okay, so now that's what the problem asks. Now it's always a good idea to draw a picture. We know that this is a paraboloid of revolution, and what we only want is the part from 1 to 4. So we're asked for the surface area of this bowl without a top or a bottom. Okay? So we're going to apply our technique. We're going to apply our technique. First of all, I need a function f which describes the surface. To use my method 1, I need to rewrite this as f of xyz equals x squared plus y squared minus z equals 0. So I just shoved z to the other side so that it looks like x squared plus y squared minus z and equals 0, and I dub this f. So I'm going to need to compute grad f, so that is 2x, 2y, minus 1. Question?
What if you shoved everything to the other side? Would you get the negative?
Okay, so if you shoved everything to the other side, you get minus x squared minus y squared plus z. And so this would be minuses, minuses, plus. But we're going to take 10 to the 11, and we're going to take the absolute value, so it doesn't matter which way you take it. We don't have an orientation problem in this particular example. It's only when you start not having absolute values that you have to worry about that. In any case, yes, indeed, the length of this vector is 4x squared plus 4y squared plus 1. And the other thing we need is the z component. So this is just z component, which is the absolute value of minus 1. So even if you don't remember what k is and just remember, oh, method, I just take the z coordinate and put it there. That's what you have to do. So what this says is the sigma is equal to grad f, length of that, over absolute value of the z coordinate dA, or dx dy. Let's just go dx dy, what the hell. And that equals this over this. Root 4x squared plus 4y squared plus 1 over 1 dx dy. And that's going to be pretty handy. Okay. So in order to attack this, we've got the big part of the piece. So by what I've said, we don't even have to change the 1, because 1 is just 1. no matter how you look at it. The d sigma we've just found out is root 4x squared plus 4y squared plus 1 dx dy. So that was very straightforward. It's 1 times this over 1. And if you like, you can cancel out the 1s or you can just ignore them. 1 is particularly nice like that. Now, the one thing is I have not told you what r is. So you have to actually, what is r? Well, you'll be lost unless you look at the picture and look at the shadow. So the shadow is r. So in some sense, you just set, for the outer piece, you set z equal 4, and for the inner piece, you set z equals 1. So the r is the shadow, which is x squared plus y squared between 1 and 4. Okay, you can see that from the picture. You either get a circle of radius 1 from the inner, this piece here goes down to a circle of radius 1, whereas this piece goes to a circle of radius 2. Or you can just get it by, as I said, plugging z equals 1, which is one extreme, and z equals 4, which is the other extreme, and to see that you have reduced matters to this double integral. So just to write that out once more and have some space to work on it, we have changed our surface integral into a double integral as follows. So we've reduced matters to seeing that the surface area is just the integral over the region x squared plus y squared between 1 and 4 of root 4x squared plus 4y squared plus 1 dx dy. Now, I didn't have to change any z's, as it turned out. Nothing had a z along this. But if it had happened to have a z, I would have been fine. All I would have done is replace it by x squared plus y squared to reduce everything to x's and y's. Now, I still am left with a double integral. How do I do this double integral? What are the two magic words? Or really only one magic word? Polar. Okay, so we're going to switch to polar. Forget surface, it's just a double integral. We're just going to do polar, and it's quite easy. Because x squared plus y squared is r squared, and dx dy is r dr d theta. You see that x squared plus y squared is r squared, so we have 1 is less than r squared is less than 4, i.e. r goes from 1 to 2. And because we want the whole circle, theta should go from 0 to 2 pi. So this integral becomes root 4r squared plus 1 times r dr d theta. And r is going from 0 to, from 1 to 2. And this is going from 0 to 2 pi. And luckily, the derivative of 4r squared is 8r. So I'm going to even avoid a change of variables by putting in 1/8 here. Also notice that 1 and 2 don't depend on theta, so I can sort of decompose the integral into the d theta piece. And the other piece, which I'm now going to write as 8r times 4r squared plus 1 to the power 1/2, just to be safe about it. And this is now one variable calculus. This is 1/8 times 2 pi times, and it's going to be 4r squared plus 1 to the power 3/2 times 2/3. Let's just do a reality check here. And this is evaluated between 1 and 2. Let's just do a reality check. When you differentiate this, the 3/2 comes down and kills the 2/3. This becomes a power 1/2, and the chain rule caused this to spit out an 8r, which I cleverly put the 1/8 there to correct for. So when all's said and done, you get 2 times 2 is 4, so we're going to get 1/6 pi times, plug in 2 and you get 17 to the 3/2, and plug in 1 and you get 5 to the 3/2, and that's it. It's disgusting, but that's it. I think that's it. I hope that's it. All right. Any questions about that example before I do method 2? All right. So that's the technique. Method 2 involves parameterization. You parameterize the surface as follows. So write S as R of u comma v. Now, to be confusing about it, sometimes little u and v are different letters. One of them might even be an R without an underline, such as, I don't know, in polar type of coordinates. Well, if that's the case, then you just have to distinguish between your R with an underline and little r which without an underline, which are completely different. Okay, so if you can write your surface as this, where uv is in some region R in the UV plane, I don't know, sometimes it's a rectangle, it's a different sort of shadow because that little thing is going to become stretched and wrapped and maybe sort of even glued together at the ends and cover the surface. So if you can write it like this, then instead of the nasty formula for d sigma from before with this gradient and the k in it, there's a much nicer formula for d sigma. It's just the u derivative, which now we're going to write r subscript u, cross the v derivative. And that's a vector. It's going to involve a cross product, and we need the absolute value of that, du dv. And that's the formula. It's a sort of Jacobian. So this is the derivative. This is another way of saying this is dr du, and this is dr dv. And that's the entire theory of that method. So all that's left is to do an example. Here's a nasty example that probably threw a lot of people in the time that it was doing. It said, find the integral of z to the n over the unit sphere, I believe. Where n is some positive integer that's constant, but you don't know what it is. Okay, so in other words, what we're looking for is this. Let's call this S. What we're looking for is the integral of z to the n d sigma. Okay, the only difference between this, we're not just looking for the surface area. If this was a 1, we'd have the surface area. But we're actually integrating a function. We're adding up the values of z to the n over the sphere. Okay, so this could be done by method 1, but you'd have to break the sphere up into the two caps, as I had said right at the beginning of that method. So instead, watch this. We're going to parameterize the sphere by using spherical coordinates. The only thing is we have rho, phi, and theta, and we don't need rho, because rho is 1. It's a unit sphere. The rho is 1. This says rho is 1 here. So we're going to take parameters as follows. My parameters are phi, which is going to go from 0 to pi, and theta, which is going to go from 0 to 2 pi. As I discussed, phi only needs to go down to pi, whereas theta, you need the full circle of 2 pi. All right. So those are my parameters. Now, the spherical coordinates looks like this. R of phi comma theta is equal to, well, normally the x would be rho sine phi cosine theta, but rho is 1. So it's just sine phi cosine theta. And similarly, the y would have a rho, but rho is 1, so it's sine phi sine theta. And the z would normally be rho cosine phi, but rho is 1. So that actually parameterizes the sphere. That parameterizes the sphere. And what we're going to need is compute the derivative. So we need r phi. The phi derivative is. So you just differentiate that with respect to phi. And you get cosine phi cosine theta, cosine phi sine theta, minus sine phi. And we're also going to need the theta derivative. So you go back up to the original one and differentiate with respect to theta instead. So when you do that, you get minus sine phi sine theta. Theta derivative here is sine phi cosine theta, and there's no theta over here, so you get 0. All right, so now we need to compute the cross product. And I'll just do the gory details, it's not so bad. I don't like doing mistakes, but there it is. So I need R phi cross R theta is equal to I, J, K, see, there's the K, cosine phi cosine theta. The J is sine phi sine theta. And no, I'm reading the wrong line. I'm trying to read the second line from that. Minus sine phi. And now the bottom line, minus sine phi sine theta and sine phi cosine theta. And this is 0. So if you compute this, what do you get? You get 0 minus, and you're going to get sine squared phi cosine theta. The j coordinate is this times this minus this times this, but there's going to be an extra minus. Well, actually, this is a minus times a minus. So if you work it out, it's that minus this, but there will be a plus. Anyway, so it becomes sine squared phi sine theta. Then what's left? The k coordinate is going to be this times this, which is cos phi sine phi with a cosine squared theta, minus minus this, and actually you've got a cosine squared plus a sine squared, so the whole thing works out to be cosine phi cosine theta. Bit of a mess. Now we have to compute the length of this. So the length is, we need, well, I'll compute the square of the length first. What the hey? So it's to the 4th phi cosine squared theta plus sine to the 4th phi sine squared theta plus cosine squared phi cosine squared theta. So what does all that work out to be? Cosine squared plus sine squared is 1. So you get sine to the 4th phi plus just the last term. There's something wrong. Where is the mistake? I just can't see it. Okay, I only need one person to tell me. Sorry, who's going to tell me? Put up a hand. Okay, tell me.
The last term of your cross product should be cos phi sine phi.
Thank you. I said it correctly. I just wrote it wrong, which is worse than saying it wrong and writing it right. Thank you for that. Now we can take out a factor of sine phi. And the whole length squared just reduces to sine squared phi. And so this means that r phi cross r theta, the length, is just sine phi. Technically, when you take the square root, you should put a plus or minus. But notice this is positive because phi is in the first or second quadrants. Okay, so why are we totally not surprised to see that sine phi? Where have you seen that before? Well, the Jacobian for spherical coordinates is rho squared sine phi. Right, but we don't have a rho because the rho is 1. So that's the only thing we're missing. So this is kind of nice. Anyway, it's been a bit of a messy computation, but now we can actually do the problem. Of course, it would have been acceptable, by the way, if you wanted to be really clever about it, you could have just said, oh, well, d sigma we know is sine phi because rho is 1. And we probably would have accepted that. but this is it in gory detail. Anyway, so now we've got to compute the integral. Here goes. Then we'll take a break. The double integral z to the n d sigma is equal to the integral of what's z? Z is, if you look back over here, cosine phi. So it's cosine phi to the power n. And then you have this determinant, sine phi, d phi d theta, and you've got to get the bounds right. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. So I want to stress that this is the d sigma. Okay, so we've reduced it to a regular old integral. In fact, it's a double integral, but the theta bit, again, you can just pull out the 2 pi. So this is going to be 2 pi times the integral of cosine to the n phi sine phi d phi. Now, here's the deal. The derivative of cosine is minus sine. So if you just do the substitution, you find that you get minus 2 pi over n plus 1 times cosine to the n plus 1 phi. And that's evaluated between 0 and pi. Okay, so the 2 pi is just from there. Just do a reality check. When you differentiate cosine to the n plus 1, you get the n plus 1 comes down and kills that. Then you have a power of n, and you also spit out a minus sine theta, and there's the minus to deal with that. So we just have a little bit more work to do, which I will do over here. This equals minus 2 pi over n plus 1 outside of what? Well, when I plug in pi, cosine pi is minus 1. So you get minus 1 to the n plus 1. But when you plug in 0, you always get 1. And that is the answer. But you can tidy it up a little bit. I'll probably have to do it over here because I feel a little bit cramped. So let's just, what's that? Yes, here it is. Minus 2 pi over n plus 1 outside of minus 1 to the n plus 1 minus 1. Now there's two cases. If n is odd, then n plus 1 is even. And this is 1 minus 1. So it's minus 2 pi over n plus 1 times 1 minus 1, which is basically 0 if n is odd. Whereas if n is even, then this equals minus 1 to an odd power, which is minus 1. So the whole thing is minus 2 pi over n plus 1 times minus 1 minus 1, which can also be written as 4 pi over n plus 1 if n is even. So that's a much more tidy way to write down the answer. Okay, question? I think you get most of the credit for leaving it in this form. I mean, you know, probably 8 or 9 out of 10. It's possible even 10 out of 10. But you have to admit that's a little snazzier just to say, oh, it's 0 or 4 pi over n plus 1. Now, by the way, there's a reason why it's 0. If you think of the function z to the n, this is an odd function of z if n is odd. So that means if n is an odd number and you're integrating over the sphere is symmetric in z. The sphere is symmetric actually in everything. Very symmetric. But the point is that whatever the z is up here, if n is odd, there's a corresponding negative version of it. That bit cancels that bit. This bit cancels this bit. And all over the whole sphere. So it's not a surprise to get 0. But when n is even, of course, you're adding up positive things, so you can't get 0. And that's not obvious that you would get 4 pi over n plus 1. But that's what you get. All right, let's take a break. When we come back, we'll do the 3 big old theorems. I've got the 3 big theorems to tell you about. And I've got about an hour and 10 minutes to tell you. Woohoo. Now, however, I still have one other thing to tell you about surface integrals that I kind of forgot. So, flux integral through a surface. and this is going to come up. Okay, so here's the idea. Instead of G d sigma, I'm going to write down something that looks like this. F dot n d sigma. Okay, this is just a special case of a surface integral where instead of this G, I am having F dot n. So what is this? Well, here's the idea. I have some of the surface could be closed, meaning it doesn't have a boundary, or it could have some boundary. Okay, and now what I want to do is take a unit normal everywhere, and there's again some ambiguity as to whether it's up or down, in or out, whatever. So there's a choice of two, and that has to be specified when you say n. So this is n is a unit normal, and there's a choice of two. Now that's only true if S is orientable. Remember, this Möbius strip thing is not orientable, because if you start defining the hairs pointing one way, when you get back to your starting point, you're actually pointing the other way, and there's a discontinuity there. So S has to be orientable for this to exist, but basically that's a technicality that can come up in real life, but will not come up in Math 201, I suspect. But it's worth putting in the back of your mind that S has to be orientable. Certainly if a question says state Stokes theorem, you'd want to be saying the word orientable to guarantee full credit. But more on that when we do Stokes theorem in a few minutes, or half an hour, whatever. Okay, so take this. Now F is some vector field, which is not necessarily normal. And remember, at every point, there's some vector in such a way that it's smooth. So if we focus on just one point, there's the n, and F could be pointing out over here. And all we're doing is taking the dot product, seeing how much it is, and that's the value at that point. And we're doing that at every point and adding them all up. That's what this means. Now, again, the interpretation is you have a whole bunch of ants sitting on one side of this thing, and they're trying to crawl through it, and the F is blowing them through, or if it's pointing downwards like this, it's blowing them away, and it's only the bit that is pointing in the normal direction of F that counts, and the dot product takes that into account. It just projects it and looks at how much of F is going in the n direction. And so we're adding all of that up, and we get the net flow of ants through or back, or if you prefer gas, through this membrane here, or this sort of artificial surface. Is more gas coming in or out if you just let it flow, depending on the direction, depending on where F is. Over here, F might be this way. Over here, it might be that way. So what's the net effect? Integral. Okay, so that's the geometric sort of interpretation, or the physical interpretation of it. But in order to compute it, you know what sigma, d sigma is. I just have to tell you what n is. And it depends if you use method 1. In method 1, which is where the surface was f of x comma y comma z equals 0, or a constant, the normal is just plus or minus, and I'll explain that in a second, grad f over the length of grad f. Now that's from pre-midterm stuff. You know, if you have a level surface, then the gradient is the normal direction. When we divide by the gradient, when we divide by the length here, it makes it into a unit. The plus or minus is just the ambiguity as to whether it's up or down. This you have to investigate to see which one. Investigate. So you just sort of do a reality check and write down a few of the values and say, oh, is it up or is it down? If it's the wrong way, you probably need a minus out front. Okay, so that's method 1. Whereas method 2, where we have the parameters, n is actually this vector that we computed, RU cross RV, not the length. That's just the normal divided by, to make it unit, you have to divide by this quantity, which we already computed, and of course the plus or minus. So you might notice that when you are going to compute an area like this, the d sigma included the bottom. Remember, d sigma was the bottom du dv. So actually you don't need to compute the length because they'll cancel out. Okay, and the same thing happens here. The denominator here cancels the numerator of the d sigma. So it might be worth making a little comment that you can save yourself one little computation of the square root piece because it will cancel out. But mostly, even if you look at the official solutions, they'll put both square root pieces in and cancel them out so you don't have to learn more formulas than you need. So you learn the n, you learn the d sigma. Sure, when you multiply the n d sigma, the denominator of one cancels the numerator of the other, but that's just fine. No need to learn two separate formulas. All right, so that's the sort of setup for surface integrals. We're not going to need that until we do Stokes and divergence theorem. First, I need to talk about Green's theorem. Any questions about that? I mean, this you know. This you know from pre-midterm. This is slightly different, but also quite believable. I mean, after all, RU is a tangent in the U direction, RV is a tangent in the V direction, so together they make the tangent plane, and RU cross RV is therefore perpendicular to both of them, so this is a normal. So this is nothing new, but extremely useful. Okay, let me tell you Green's theorem. Nicely enough, the whole theory fits in about 3 to 5 minutes, depending on how slowly I talk. But it's the problem. More theory left. Just need to know what the theorems say. And Green's is actually the most intricate because it has two versions. So here's what it says. So first of all, it's a two-dimensional theorem. We're working in 2 dimensions here, and the setting is as follows. So we have a closed, simple curve, C. So closed means there's no endpoints, it's a loop. And simple means it doesn't cross itself. Okay, so you're looking at something like this. Okay, it has a counterclockwise orientation. So it's in the plane with a counterclockwise orientation. Now, there are some technical issues about how smooth the curve is. Basically, it has to be smooth everywhere, except that it can be made up of pieces which are smooth. So you could have, for example, a square that has 4 pieces which are smooth, but the corners are not smooth. So technically, C should be piecewise smooth. That's a technical condition. But I don't want to have something like this that has no derivatives everywhere. It's possible to make such a thing, but you have to kind of be really clever to find a function that's not differentiable anywhere. All right, so basically everything you're likely to see. And this C encloses R. All right, so then there's 2 versions. Version 1, which I'll call flux divergence version. If you remember flux dive somehow, and I'll give you an idea of how you might remember that in a few seconds when I do version 2. If you do flux divergence, this is what it says. So if you consider the flux integral of a vector field F, and we looked at this integral right at the beginning. I showed you exactly how to compute that, in fact, in a specific case. Around C, this is equal to the double integral of the divergence. Okay, so in my regular classes, and you can look back on the video if you care, I did some things about ants or marbles I think I used at the time, and just tried to describe why that makes sense. Why the flow out of the region is the sum of the divergence of the flows everywhere inside. But I'm not going to do that. I'm just going to say, okay, here it is. There's the formula. Sorry, I don't have time to really get into what it means. But I do want to say that it is a fundamental theorem of calculus in the sense that the integral of a derivative in a region, this is a derivative, the integral of a derivative is actually equal to the values of the function on the boundary. Okay, so this depends on the derivative of f inside, whereas this only depends on the values of f on the outside, which happens to be a curve. Okay, so it is a fundamental theorem of sorts. Okay, now in order to apply it, there's an alternative version which kind of expresses it in a nice way. If f is equal to m comma n, so if you write it as some sort of function of xy and another function of xy, then you can express this normal as we did earlier. Remember, n ds you somehow thought of as dy comma minus dx. I wrote that formula up earlier. So you can change this by taking a dot product of those two as follows. So m dy minus n dx equals the double integral of the divergence. But the divergence is just dm dx plus dn dy. Dx dy. So this is an extremely concrete version of that. Where's it gone? All right, so that's version 1. Version 2 is almost the same in a sense. Version 2 is the circulation curl version. So maybe you can remember circulation goes with curl because C and C, which would mean that flux goes with divergence because they don't match. That's all that's left. So it's very similar, but instead if you start with a circulation integral f dot dr, well, that is equal to essentially the integral of the curl. But there is a little technicality in that you have to do a dot with the k. And again, k is 0, 0, 1. So when you compute that curl, you only look at the z coordinate of it. So this is the z coordinate of the curl. That's the geometric interpretation. And that is the second form. Again, it has a nice version if f is m n, and then dr, as we saw, is just dx comma dy this time. So the left-hand side in the differential form is m dx plus n dy. And it turns out if you compute the curl by doing this, I, j, k, d dx, d dy, d dz, m, n, and 0, because f is m comma n comma 0. If you compute this, and remember that m and n only depend on x and y, so there's no d dz component, you find that the z coordinate of the curl looks like this. It's the double integral. I always get this wrong, so let me just look it up. Yep, it's dn dx minus dm dy. Dx dy over the region R. And that's the other form of it. So I recommend learning all 4 forms, or really both the forms and both the form each form. Okay, so that's the basic theory. Now, before I do an example, I'm just going to tell you one little bit of an extension to this theory. And that is, you can apply it to a region with holes, as long as you get things correct in terms of direction. And this is going to be a common theme, because it also applies to the other 2 theorems. So this is kind of important and subtle. So the one little extra bit of theory is how to deal with holes. So suppose your region looks like this. So here is my r. And I need to have a correct interpretation of c. So the correct interpretation of c is that c in this picture is the union of c1, c2, and c3. And you just have to put the correct orientation on. So the orientation, if it's counterclockwise, here's how I imagine it. I'm walking along in this direction, and everything that I care about is to the left. That's it. Everything is to the left. So this is not going to be true if I walk along here. If I walk along here this way, no good. The hole is to my left. I need the nice flat surface to be to my right, to be to my left. So I have to go around clockwise. So in other words, in the holes you go around the other way. That is the correct orientation. So for any holes, you have to go clockwise, in other words. Okay, so in this case, the left-hand integral, this f dot dr, or the line integral, has to be broken up into three integrals. C1, C2, going that way, C3, going this way, each of them with an f dot dr. I didn't write them out 3 times. Okay, or you can do everything counterclockwise as normal, but then you have to reverse the sign of any of the holes. So I call this C1, I call this C2 in this area. I forgot to label that. Of course, you might not have any holes. You might have only 1. You might have 3. I mean, whatever. But in this case, so these are supposed to go the other way, whereas this goes the normal way. If you want to write them all as clockwise, then you have to reverse the sign in front of any ones that go clockwise. Then you make them counterclockwise. Okay, so that's just one caveat. Sometimes you have to apply this thing in a hole. Question?
So for this, you can't use Green's theorem, right?
Oh no, you can use Green's theorem.
Even though the region, how do you, like, what's the R you integrate?
Well, the R that you integrate is just this. There's no problem with the R. It's just, you know, you can integrate over areas with holes. We did one with an annulus earlier, you know, where R went from 1 to 2. Remember that one? Little r in polar coordinates.
Have weird limits.
Yeah, I mean, it'll have weird limits, although in polar coordinates the annulus had very easy limits, 1 to 2 and 0 to 2 pi. The difference is you have to correctly interpret the line integral. Where here I did the f dot dr, but also it applies to the f dot n ds version. Okay, so this will make more sense when we see some examples. So I want to look at a couple of examples of Green's theorem before moving on to Stokes' theorem. So let's see, how much time do I actually have? Not a lot. Okay, so here's an example. C is given as follows. X is 1/2 sine 2t, and y is equal to sine t. And t goes from 0 to pi. So the first thing to notice, by the way, this is a closed loop. Why is it closed? You plug in 0, you get 0, 0. So it begins at the origin. If you plug in pi, you get sine 2 pi is 0, sine pi is 0. So you actually begin and end at the origin. So it's closed. And so the question is to find this. It's given in differential form. X dy minus y dx. Find that. Well, we're going to do it directly. It's very tempting to use Green's theorem, but part B says use Green's theorem to find the area inside that region. So we won't use part A. Let's dispute this directly. But it's not so bad. Here it is. We have x is 1/2 sine 2t. So dx, the 2 comes out and you just get cosine 2t. On the other hand, y is sine t. So dy is cosine t dt. And I just noticed I left out the dt here. dx is something dt. Okay, so this integral becomes the integral from 0 to pi, because that's the value of t. And look how easy this differential form is to deal with. X is a half sine 2t. dy is cosine t dt. I'm going to hold off the dt till the end. Minus y, sine t. Dx is cosine 2t. And it's all that dt. And that's a regular old integral. And if you want to do it, which you do need to do, you need to write sine 2t as 2 sine t cosine t. Double angle formula. So I believe you get sine t cosine squared t from that. Minus sine t, and then you have to do a silly thing again with cosine 2t. You want to write that as something like 2 cosine squared t minus 1. That's all that dt. So you have to do a bit of work. I think I did that bit of work. No, I don't remember what it is. I'm going to call it A, and you find it. No, I'm not going to call it A. I'm going to call it B. Just a regular old integral. I don't feel like doing it. Okay, so that's part A. So the next part says, find the area enclosed by this curve using Green's theorem. But even if it didn't say using Green's theorem, all we need is to use the first form, the normal form, if you like, that I erased. So we just need this fact that m dy minus n dx is equal to the double integral of the divergence, which is dm dx plus dn dy dx dy over the region. So that's just quoting the formula that I wrote before. And you see we have something dy minus something dx. All I have to do is replace m by x and n by y. And then on the right-hand side, you'll get dx dx. And n is y, so you get dx dx, which is 1, plus dy dy, which is 1. So you get 2 dx dy. So that was convenient. But this you just computed as b. This is whatever this number b was that you found. So twice the area is b, so the area is half of b, whatever b turned out to be. I think it might be 4 pi, if I remember correctly. And so the area was 2 pi. But maybe I'm wrong. Maybe that's not it at all. Okay, so any questions about that pretty straightforward Green's theorem question? I say pretty straightforward because there are no holes. You didn't even have to deal with the non-differential form. Everything just sort of was in the nice form that you wanted it in for optimally easy computation. In part B, how did I know to use version 1 instead of version 2? Well, it was something dy minus something dx. But in reality, I have to tell you there's no difference between the versions. If you rewrite this as minus y dx plus x dy, and call that m and that n, and use the other form, you'll get exactly the same answer. The two forms of Green's theorem are exactly quickly equivalent. Just one goes into the other, but they have different physical interpretations. So if you can use one, you can always use the other. All right, bit of restlessness. Is that bad? Is that a hard problem? If you think it is, check this one. All right. This is sort of similar to one we saw earlier. Okay, that was not a cue for speech. Oh my goodness. Can't do any 3-hour review sessions with you guys. You just crack. Well, my friends, I have news for you. The final is 3 hours, so get used to concentrating for it. Okay. Why do you think I do these 3-hour sessions? It's to prepare you for the 3-hour exam. Actually, because I didn't have any time on last week. Okay, so anyway, so f of xy is this. That's given, and you might notice it's pretty similar to one of a previous example. And so the question is to find the outward flux. Find the outward flux through, and there's three parts. First part is x minus 2 all squared plus y minus 1 all squared equals 1. Second part, x squared plus y squared equals 1. Third part, x squared over 4 plus y squared over 9 equals 1. Okay, so there's three different C's here. I'm going to call this C1, C2, and C3. We have to do them individually. Okay, so for part 1, first of all, let's just draw a graph of the C1. So x minus 2, y minus 1 is 1. So the center of this circle is 2, 1, and the radius is 1. So it looks like this. No, does not look like that. It looks like this. Now, again, it's sort of important to note that this function f has a singularity here. This is a singularity. So actually, you cannot use any Green's theorem on any loop containing a singularity. But this loop does not contain a singularity. So according to this, we want the outward flux. So the outward flux is f dot n ds. Remember, that's a flux integral. So you have to know that this is flux. You absolutely need to know it. Flux, normal. Circulation or flow would be dr, tangent. Okay, so we need this integral. And by Green's theorem, this is equal to just the divergence of the period here, which I'll call R1. So this is R1. So we have to compute the divergence of f. So the divergence of f is the derivative 2x over x squared plus y squared plus the y derivative of the y component. And if you actually do the computation and you need the quotient rule, you'll find that you get 0. You'll find that you get 0. I'm not going to do it. It's a straightforward quotient rule times 2. Actually, once you've done this one is symmetric. Switch x and y around and you'll find it all works out very nicely. Okay, so you get 0. So basically, this is now the integral of 0, and that's the answer. The denominator is 0 only when x squared plus y squared equals 0, which is at the center, at the origin. Okay? So if the denominator is 0, then the function is not defined, and by definition, that's a singularity. You might, if it's a removable discontinuity, you can probably survive. But you know, that's clearly not the case here. All right, so you might ask, well, why aren't they all 0? And the answer is, as you suspected, that the problem is the second curve is just the unit circle and it encloses the singularity. No good. So to do the second curve, we have to whip out an integral very similar to one we've done, and we have to do it directly. f dot n ds for C2, no Green's theorem. C2 encloses singularity at the origin. So that does not allow us to use Green's. So technically, I didn't even state that in Green's. I said it has to enclose a region, but I should say in the statement that f has to be defined everywhere in the region. And it's certainly not defined here at the origin. So we have to compute it directly. And we compute it in the standard way. We take a parameterization. X is, so R is cosine t sine t. And therefore n ds is dy comma minus dx. So this is x, this is y. So dy is cosine t, minus dx is minus minus sine t. Also, the vector field f is 2x, which is 2 cosine t, over 1, because x squared plus y squared is 1. And the y coordinate's similar. This is very, very similar to what we've done before. So we're going from 0 to 2 pi. This dot this is 2 cosine squared plus 2 sine squared, which is just 2. I'll write it out as 2 cosine squared t, 2 sine squared t dt. That's just 2, and so this works out to be 4 pi. Okay, so there's nothing very interesting about that, no application of Green's. The interesting one is the last problem here. So we're now working over the ellipse, which goes 2 minus 2, 3 minus 3. So that's C3. And we want to have f dot n ds again, but this time over C3. Okay, so to deal with this, you could do a parameterization and recalculate it, but you're going to run into all sorts of problems. And the reason you run into problems is because the denominator x squared plus y squared is very nice when you're on the circle. It's just 1. But it's really ugly when you're on this ellipse. So actually, the ellipse is a bit of a red herring. What I'm going to say is now, the way I'm going to solve this applies to any curve that encloses the origin once. And I'm going to get the same answer as the circle. So watch this. I'm going to define a curve C by itself without a thing. Consider C as the union of C2 and C3. But I want C2 backwards, as in clockwise. No, not, yeah, C2 clockwise. Okay, here's the full picture. It looks like this. We have the circle of radius 1, but going this way. So that's C2. And then we have this ellipse going in the normal way, clockwise, C3. And I propose to apply Green's theorem to this region here with a hole. And there's no problem because there's no singularity, it's in the hole. That's okay, as long as we get this orientation going the other way. So, according to this, Green's theorem, the integral around C of f dot dn is equal to the double integral of the divergence of f dA over R, where R is this weird shape region here. But we computed that the divergence of f is 0. We've computed this as 0. As long as you're not at the origin, the divergence is 0. So this is equal to 0. So now, let's look at this integral as a line integral with two BCP. What this is the integral, so we have proved that the integral of C3 f dot dn plus the integral going the other way of C2 happens to be 0. Now we computed C2 going the correct way to be 4 pi. But if you go the other way, it's minus 4 pi. So this is equal to minus 4 pi opposite direction. And then this means that the integral we want is 4 pi. Okay, so it's a bit subtle. It's a bit subtle. If you're going in the same direction, they have the same value, because one of them has to be the opposite. So that, instead of saying A plus B, it's actually A minus B equals 0, so A equals B. And it doesn't matter that it's an ellipse. It could be anything that's around the circle. In fact, it could be anything inside the circle as well. And if you're clever enough, it could be anything at all that goes around the loop, even if it did this. You just have to chop it up into many little bits. Okay, any questions about that? You see the argument? The one you know that you computed directly. This is a very common theme, and we'll see it when we do Stokes' theorem pretty much now. Very common theme. You have this nasty thing, so you write it's in terms of another one which you can know plus an area integral which is often 0, or at least easy. Any questions about that? Yes?
Why did you write dn instead of nds?
Oh, because I made a mistake. Thank you. Please change all these dn's to nds's. Thank you for pointing that out. All right. We have to go on, I'm afraid. We have to go on. Stokes' theorem. Stokes' theorem is quite a similar setting to Green's theorem, but instead of having a region in the plane, you have some surface in space. So we've got a surface S with a boundary C. Now again, the technicalities of the surface is that it has to be smooth. So it could be like a cube or a bit of a cube or something. It doesn't have to be all smooth. It just has to be made up of smooth panels, as it were. Now, you've got to have a unit normal to S compatible and a direction on C which are compatible. These two things, there's ambiguity in each. The normal could be up or down, or in or out, whatever, and then C could be that way or that way. And so there's a choice of two in each one, and there's a compatible choice and an incompatible choice. Right? So it's like south poles and north poles and all that sort of stuff. Okay, so check this. Check this. Suppose your surface is like a cap, like this. And here's the boundary. So I'm thinking of it as the surface is on top of there. So you can either have a normal like this or the other way. So suppose you want this normal, the one pointing up. The question is, what is compatible as you're on the boundary? Which way do you want to go? That way or this way? And again, here's the deal. You want so when you're walking around, to your left, the arrows go up. That's one way of looking at it. As you walk around, you want the trees to be up. So here's an example which is bad. If the arrows are pointing that way, and you're walking around that way, I'm walking around, here's the surface on my left. The surface has got to be on my left if the arrows are going down. But here the arrows are going up. Here, the arrows are going down. So I have to walk the other way. So that when I walk the other way, okay, then if I'm standing on the bottom of it, walking the other way, so upside down, the surface is on my left with the arrows going up. Another way of doing it is to use the right-hand rule. This is the more common way of doing it. So what you want is as you move your thumb around in the direction that you're moving, your fingers come around and point in the correct direction. So in this case, they want to point this way if you're going around like that, not downwards. Over here, this direction, look, I'm going this way, so when I come around, when my fingers pierce the surface, they're actually going through the surface. If I was going this way, then my fingers would actually start outside the surface and come back around the back of it, through it, and so I'd have to be pointing in. It's kind of hard. I've seen people dislocate their wrists in exams trying to get this, so be a little physically careful there, especially if you are an athlete or a musician or something, or an artist, or actually anyone. Pretty much, I mean, you know. It says, oh, and by the way, S has to be orientable. I should say, S orientable. Otherwise, there's no unit normal field N. So here's what Stokes says. So if you want, there's this flux integral, and I showed you how to compute it in principle. This is equal to, hell, that's not what it says. It's the flux of the curl, and I want to write it the other way. Let me be very precise. want to write it the other way. F dot dr around the boundary C with the correct orientation. You take the curl of F and you take the flux of that. Okay, so this is the circulation of F around boundary, whereas this is the flux of the curl of F through the surface, through the surface. So it's another fundamental theorem. This is the derivative of F, effectively. So we're adding up the derivative of F in the interior, which is this surface. And this is saying that this is related to the values of F added up around the boundary. You have to be a little careful about the way you're adding them up. But basically, the overall flow of the curl through the surface is equal to the circulation of the field around the boundary of the surface. That's what it says. So it's a physics thing once again, but it's just one formula. It reduces to Green's theorem in the flow version because if you're working in the plane, F dot dr should be the curl dot k. But if you're in the plane, then the normal is up. It is k, 0, 0, 1. So actually, if you can remember this, then the Green's theorem version 1 is exactly, version 2, I guess, is exactly this, but with n being a k. And the d sigma is just dA, very simply. When the surface is just a splodge in the plane, then everything is nice. So this is basically Green's theorem, but boom, in 3 dimensions. Okay. Now I just have a couple of things. Similar treatment of holes. Your surface can have a hole or two in it, as long as, so this is no longer a region, but it's supposed to be a surface, as long as you go one way on the outside and the opposite way on the inside, so then everything works out. Another point is you need to be able to state so basically you need to say if S is orientable with boundary C, unit normal to S called N a unit normal to S, and a direction on C which is compatible, then this is true. And you might want to say that F is defined everywhere. F has no singularities. And then you need to produce the formula. So that would be a full credit state Stokes theorem. Now, here's the important thing. It only works on a flux integral involving a curl. Of F. So in other words, if you just have, if you want to use either Stokes or the divergence theorem, which I haven't talked about yet, but if you want to use either of them to do something like this, that's a flux integral. Stokes involves a flux integral, but it's not just an ordinary flux integral. In other words, to use it, you have to be able to write, to use Stokes, must write F is the curl of G. And G is hard to find, basically impossible in general to find. So probably need the divergence theorem, which doesn't require that. Divergence theorem. Okay, so that's a comment. I have occasionally seen a question saying, here's a vector field F, and you want to compute this. Part 1, consider G. What is curl G? And you go and work it out with the determinant, and amazingly you get F. Well, as soon as you're there, you can replace F by the curl of G and complete the question. But in general, just given an F dot n, I have no idea how to replace that with a curl of something. So probably you can't use Stokes. Okay, so just really bear that in mind. Stokes, if you start with this, then you probably can't use Stokes. If you start with this, then you can, and you compute this. So it's you can use it both ways, but it's mostly used to get from the left to the right. As in, you want to find the thing on the left, and you work it out by finding the thing on the right. So you find this by finding this, as opposed to the other way around, because mostly you're not interested in the flux of the curl. All right, any other comments? No, that's it. Everything else is balls. That's the theory of Stokes' theorem. Not so bad. Okay, time 10:05. Excellent. I'm going to do a couple of problems, then I'll do the divergence theorem and a couple of problems, and then we'll be done. All right, my friends, here goes. S is given by the surface z equals 9 minus x squared minus y squared above the region x greater than or equal to y greater than or equal to 0. Okay, so let's just draw this region. So here's x, here's y. They're both positive, so we have to work in the first quadrant. And if x is bigger than y, we have to be down here. So it's just this quarter. It's like an eighth of the entire plane. And then this is a paraboloid of revolution. So we're actually just cutting out a slice like this. And at the bottom, it will be 3. So it's this paraboloid. So S is just this curved bit of the surface. It's like a bit of an orange. And this is 9. How did I know it was 3, 3? Because 3 squared is 9. All right. So the paraboloid, the complete paraboloid, looks like this. Revolved. And in the xy plane, it's this circle here. All right. So what are we going to do? We are given that F is a vector field as follows. X minus y squared, x squared, z. And C is the boundary of this. And it says that the direction is counterclockwise from above. When viewed from above. So this is an above view. We're seeing the top of the orange as opposed to from below. And we've got to go counterclockwise. So that's the orientation. So this is C. 3 curved segments. And the answer is, the question is to compute the circulation. As in, find the circulation of this vector field Okay, so this is absolutely ripe for using Stokes' theorem. You've got a surface with a boundary, as opposed to the divergence theorem, which we will do, and we'll see you need the surface to be closed. So here, it has a boundary, and we need a flux. So according to Stokes' theorem, this is just the surface integral of the curl dot n. So it's the flux of the curl, d sigma. So we've replaced a nasty line integral by a maybe nasty surface integral. The line integral, we would have had 3 pieces to deal with. 3 different line integrals, 3 parameterizations, yuck. Who knows if we could have even done it. But maybe the surface integral will be nicer. So in order to continue, let's just compute the curl of f. I don't remember what it is, so I'm not going to cop out on that. Actually, I'm going to compute it. Maybe I never even worked it out earlier. I'm going to work it out now, so hopefully I won't make a mistake. Here goes. Curl of f is equal to ijk d dx d dy d dz, and now I copy in my f from the question, x minus y squared, x squared, z. That's what it is. Okay, so the I component is the derivative of this, which is 0, minus the z derivative of x squared, which is 0. Nice. The j derivative is minus the x derivative of z and the z derivative of this, another 0. The k component, on the other hand, you get d dx of x squared, which is 2x, minus d dy of x minus y squared, which is minus 2y. So I believe the is 0, 0, 2x plus 2y. All right. So, according to that computation over there, we just need to work out what n and d sigma are. So we're doing a surface integral, and I'm going to use method 1. I mean, there is a parameterization using some polar stuff, but you might as well use 1. So the surface is, let's put everything on the left-hand side. We'll say f is equal to x squared plus y squared plus z minus 9 equals 0. Or you can leave the 9 on the other side. It doesn't affect anything because all you care about is the gradient. The gradient is 2x, 2y, 1. And the gradient in the k direction, in the z direction, is just 1. All right, so according to my computations, n is either plus or minus grad f over its norm, which is plus or minus this, 2x, 2y, 1, over the square root of 4x squared plus 4y squared plus 1. Okay, so is it plus or is it minus? This is the key thing. You have to look at the sign of 2x, 2y, 1. So what does that vector look like? Remember, let's come back over to the diagram. X and y are both positive. So the vector 2x, comma 2y, comma 1, never mind the stuff on the bottom, this is going to have z coordinate going upwards, because it's 1, and x and y coordinates are also positive, because they are here. So this thing is definitely going to go up and out. It's sort of hard to draw. It's actually coming out of the board. So this is correct. If instead you had written f is 9 minus x squared minus y squared minus z, which you could have done, it's just the negative of this, you would have gotten minus 2x minus 2y minus 1, which would point down and in. And then you'd have the minus. So as it happens, we need the plus. That's what we need. Okay, so we now know what n is.
So n depends on f, on how we write f?
Well, no, it doesn't depend on how you write f. So the question is, does n depend on which way you write f? And the answer is not really. I'm saying if you wrote f with the negative, then you'd have to take the negative of it to get the positive. So n has to be the plus, whatever it is. In the other case, it would be plus or minus, minus 2x, minus 2y, minus 1, and then you'd have to choose the minus to get rid of the minuses. So it doesn't depend on it. All right, so, but on the other hand, it does depend on the question saying that the normal that you want is the one that's upwards. Okay? Is that what the question actually said, by the way? No, I've skipped a step. I have completely skipped a step. The problem just told me which way the circulation does, so I need to use the right-hand rule to see it's the outward normal. Okay, I put my thumb there, and I go through the orange when I curl my thing up and out. So yes, I do want the outward normal. Okay, so n here, n is the outward normal, up normal. So 2x, 2y, 1 over root 4x squared plus 4y squared plus 1. But on the other hand, d sigma is equal to norm of grad f divided by norm of grad f dot k. And grad f we worked up over here, so that's the same norm here, 4x squared plus 4y squared plus 1 over the absolute value of 1. And so we can put together our integral. I'll do it over here. So we computed the curl was 0, 0, x, 0, 0, 2x plus 2y, dot the normal n, which I'm going to pull up from there as 2x, comma, 2y, comma 1 over root 4x squared plus 4y squared plus 1. And then I need the d sigma, which I computed as well, is 4x squared plus 4y squared plus 1 dx dy. And in my hurry, I left out over here the dA. So come back over here, and you need a dx dy to make that work. All right, so you see how I packed it all together? I computed the curl directly. I did the normal by grad f over its norm, and I did the surface area by the norm, which of course cancels, always should, over 1, which was the k component. And now I have to complete the integral. The dot product in here is quite simple. It's just 2x plus 2y. Right? Because the 0 integral reduces to 2x plus 2y dx dy. But what is r? That's the only thing left. What is r? R is the shadow, which in this picture is just this wedge here. So R looks like this. From 0 to 3. So in polar coordinates, x is cosine, well, x is r cosine theta, and y is r sine theta. Dx dy is r dr d theta. R goes from 0 to 3, and theta goes only from 0 to pi over 4. It's just the positive wedge, or half of the positive quadrant. And that's now a very simple integral, and I'm going to leave it for you. We've already done polar coordinates. So, all right, so that's that example. So no doubt you will have other examples of Stokes' theorem, but I kind of need to move on to the divergence theorem in my last 13 minutes. Okay, so again, tomorrow we'll have plenty of time for questions, and I fully expect to do every Stokes' theorem question in the entire past final pantheon online. I'm not saying I have to, but I wouldn't be surprised if we end up doing them. So just so you know. But right now we have some time limitations. So here I really want to do the divergence theorem. So here it is. Divergence theorem. The setting is as follows. Now you have a surface S, which is not only orientable, but it's closed. No boundary. All right? And it's the outward normal. So now there's no ambiguity. It's got an inside and an outside. It's like a sphere, or some lumpy version thereof. It's got an outside and an inside, so there is N. And again, S should be piecewise smooth. It doesn't have to be smooth everywhere. It can have panels that are smooth. All right. Now, here is what the theorem says. This time you start with a flux integral. So this is the outward flux. And notice that it's not the flux of the curl. It's just the flux of F. Outwards flux of F through S. So this is equal to the triple integral over the inside. So let's say D is the inside. And it's the divergence, of course, because it's the divergence theorem, dV. So it changes a flux integral into a divergence integral. Volume integral. All right. Comments. You have to know how to state it. There's a similar treatment of holes. So let me explain how to deal with holes here, if you have them. So I want you to think of, this is a thick shell. I want you to think of this in 3 dimensions. It's a thick shell with a hole in the middle. And remember, when you pick it up, you can't see the hole. The hole is inside this object. It's completely embedded. But you can maybe tell by tapping on it and hearing that it's hollow. Okay? So you have this. The outward normal has to look like this on the outside, but when you're on the inside, it has to point inwards. But it's still an outward normal, because if you stand on the surface in the inside, then n has to point away from the surface. This cannot be the outward normal here, because it's actually going into the metal. Okay, so just beware that holes are treated by reversing the direction of the n. But there's no problem here. It's just a volume integral. Okay? Now, before I do an example, I just want to say that there is an exceedingly common type of question, and in fact the one example I'm going to have time for is exactly this sort. Here is a common technique, common use. If the surface is not closed, so it has a boundary, then sometimes you can complete it. So you find S1, another surface, so that S and S1 together is closed. So think of it as a lid. You put a lid on it. And I'll show you an example. Well, then you go like this. You want to find the flux over this integral S, over the surface S. But you add this up with the new flux integral, and then you can apply the divergence theorem, div f dv. Okay, so what's the point of this? This is what you want. Maybe this is easier. And then this is easier. So in order to find this, you find this and subtract that from that. Okay, that's a very, very common sort of question, and here's an example of exactly that. Out of all the divergence theorem questions, probably 2/3 that I saw in the past exams followed that same template. So it looks like you might want to use a Stokes theorem, but you cannot. It looks like you can't use a Stokes theorem because you won't have a curl. You'll just have an F. On the other hand, it looks like you can't use the divergence theorem because you not have a boundary. Then you need to find a lid. So let's quickly do one example, and then we're going to have to stop. We have 8 minutes to do this example. Okay. You are given a vector field F, which is this. X cubed plus sine y, y cubed plus e to the z, z cubed minus 1, your standard disgusting mess. And the surface S that you care about is the hemisphere x squared plus y squared plus z squared equals 4, and z equals 0. Or z greater than 0, rather. N points away from the origin. And the question is, find the flux. Okay, so here's the picture. We have the hemisphere like this, and the radius is 2, and we only want the part of the hemisphere above it, above the axis. So there's S. Okay, we can't use Stokes because we want the flux, not the flux of the curl. There's no curl here, so can't use Stokes. unless we were very clever and found a G such that f was the curl of G. We can't use the divergence theorem because S is not a closed surface. However, the lid in this case is the base of it. So let S1 be just the interior of the base circle. So it's the interior of x squared plus y squared equals 4, and z equals 0. So now, S together with S1 is a closed surface. You see it? S is the hemisphere. S1 is just this circle in the xy plane, the interior of the circle. Now, let's be careful about the normals. Which normal do we want? The question says we want the normal away from the origin. Okay, so that means that when you're on the bottom, the normal points down. So the bottom is flat, the normal always points down. Because that's outside. Very careful, that's a little trap, is that you want the normal to point down, not up. If it points up, it's pointing into the surface. So I'm now going to call D the interior of the hemisphere. So according to the divergence theorem, we now have, and this is the same template, S together with S1 completely enclose this D. So we have the flux through S plus the flux through S1, which is the base. And I want to point out that this is downward, as we've seen. This is equal to the divergence of F, the triple integral over the interior. Okay, if you leave this out, that's not a correct statement because the surface would not be closed. It doesn't, just the top of shell does not enclose the D. So that's critical. Now, this is what we want. So in order to deal with it, we have to compute both of these things. Let's deal with the right-hand one first. So I'm going to leave a blank here, and I'm going to deal with the divergence of F. So I have to look back at F, and maybe to save some time, I'll come back and just compute its divergence over here. Div of F, I just take the x derivative here, and I get 3x squared, plus the y derivative here, 3y squared, plus the z derivative, 3z squared. Well, that's convenient. Isn't that nice how that worked out? So the divergence integral looks like this. So it's the triple integral over the sphere. So it's x squared plus y squared plus z squared less than or equal to 4, but z greater than or equal to 0, of simply 3x squared plus 3y squared plus 3z squared dx, dy, dz. Okay, so clearly we've got to use spherical coordinates because it's a sphere. If we do, this is just 3 rho squared. That was the nice convenience there. And then the thing becomes rho squared sine phi d rho d phi d theta. And we just need to work out which bits we want. Well, if you look at it, we just want the top part of the hemisphere. So rho is going to go from 0 to 2 because that's the radius of the thing. And sine phi, or phi, is going to go from 0 to pi over 2, not all the way down to pi because we only want the top half. And theta has to be all the way around from 0 to 2 pi. And this is not such a hard integral to work out. That's at 2 pi in the shadow. It turns out to be the theta integral is just 2 pi. I happen to know the integral of sine pi is 1. And this is rho to the 4th. So it'll be 3/5 rho to the 5th between 0 and 2. So that is 6/5 times 2 to the 5th. which is 192 over 5 pi. And so we can now fill in this piece. But we still have to work out this other integral. So this is the last piece of the puzzle. Once we do that, other integral will be done. But you'll see it's not a very hard integral. Unfortunately, I just erased f. Damn it. That's exactly what I wanted. So here it is again. So I need to find this integral here. It's this quantity over here. I need the integral of S1 f dot n d sigma. But this is not very bad. And let me show you why. It's just an integral in the xy plane. So you don't need to go either method 1 or method 2. You just have to write this as the double integral. D sigma is just dx dy. That's the point. It's a surface, but it's flat. F on the plane, when z equals 0, f is x cubed plus sine y, comma y cubed plus 1, comma minus 1. Because z equals 0. So this is f with z equals 0. And then dot the n, and it's 0, 0, minus 1 dx dy. Why is it minus 1? Because it's downward normal. Downward. This is where you've got to be careful. If you put 0, 0, 1, thinking that the normal is up, you will get the wrong answer. Anyway, this is over the circle x squared plus y squared less than or equal to 9. That's the base. And so this is actually just the integral over this region of 1. See, this times 0 plus this times 0 minus 1 times 1 is 1. So it's just the area of the circle. So it's area of circle radius 3, which is 9 pi, pi r squared. So, oh no, it's not 3, is it? Why am I saying 3? It's always 2. The problem is x squared, it's 2. So it's 4 pi. You can come over here and you get 4 pi. And this is what you want. Plus 4 pi equals 192 pi over 5. So the ultimate answer is, so you solve and you see this equals 192 over 5 pi minus 4 pi, which is 172 over 5 pi. End of the story. Okay, I can't take any questions because it's 10:32 and we're probably out of tape. So tomorrow, 7:30, try next door and see if it's in here. I want it to be in here, and I'm going to do my best to make sure it's in here. All right, see you tomorrow. Thanks.